I promised you to show a method to solve equations of motion of the model, but in rather implicit form. Namely, if we consider such matrix A, which depends on time, the matrix of the following form: x naught minus 2t L naught, where x is diagonal matrix, x naught is diagonal matrix with diagonal elements whose diagonal elements are initial coordinates of the particles. And x without naught will be the same, but where coordinates depend on time, according to Moser dynamics. And L naught is Lax matrix of the model taken at the initial moment of time. So I remind you that matrix elements of this matrix are minus 1/2 x I dot. These are diagonal elements, and non-diagonal elements are as follows. L naught is the same, but all entries are taken at the time 0. The statement is that eigenvalues of this matrix A as functions of time move according to equations of motion of the Moser model. This is a quite remarkable statement, because this means that observing this, we managed to linearize the dynamics. So this dependence on time is linear, free motion, but in the larger space, in the space of matrices of size n. So this is n squared. The dimension of the space is n squared, but the dimension of the original phase space is 2n. So n squared is much larger than 2n, so this is larger space. And in this space, we have free motion, linear in time, and projection of this motion onto some subspace gives already non-trivial motion, which is nonlinear and is described by the Moser dynamics. The simplest example of this is just if you consider the plane and motion, take some line, straight line in this space, and suppose some point moves in this line linearly in time. This is a trivial dynamics, but if we project it to the radius, then the dependence of this radius on time is already non-trivial. It's some complicated function. Maybe in this case it's not so complicated, but still not linear. Of course, the line, we assume that the line does not pass through the origin, because if it passes through the origin, the motion is trivial, is still linear. But if not, then some non-trivial motion. And something like this happens in this more general case, but already in higher dimensional space. So we should prove this statement. because it's not obvious. How we will prove it? First of all, let us diagonalize this matrix. Namely, let V be a matrix which diagonalizes this matrix. Oh no, excuse me. Let me write it in this way. V is matrix, the matrix which diagonalizes this. X is diagonal matrix with diagonal elements are coordinates of the particles as functions of time. This matrix V is defined, there is some freedom in its definition, because if we multiply it by a diagonal matrix from the right, this diagonal matrix will cancel, because here it appears here and here. Here's to the -1. So the x is diagonal, so they commute, and this matrix cancels. To fix this freedom, we impose the condition that action of this matrix V to the vector E, which with all components equal to 1. So that acting to this vector E, it sends it to the same vector. This completely fixes the freedom in the definition of this matrix. And of course, I mean transpose, because this is column vector. Let us show that L, another way, introduce a matrix L in the following way. Yes. And show that this matrix L is the Lax matrix of the Calogiera-Moser model at the time t. L naught is the Lax matrix at 0 time, and this one is what we called Lax matrix at the time t. How we will do this? Let us note that the matrix L naught is characterized by the following commutation relation, where the matrix E is the matrix whose all matrix elements are equal to 1. Indeed, let us calculate the left-hand side. It is, if you take the commutator, we have, and write this equality in matrix elements. We have x I minus xj, I will write not here, times L naught ij, and on the right hand side we have know that diagonal elements of this equality are equal to 0. So this, if we take diagonal elements, we have 0 in the left hand side and 0 in the right hand side. So this equality is non-trivial only in non-diagonal elements. So this we assume that I is not equal to j. Then in the right-hand side we have minus j. So we have that non-diagonal elements are just minus j divided by this difference. This is just what we have here at the initial moment of time. The diagonal elements are not defined by this condition. In fact, and now we are going to show that this matrix A defined by this equality satisfies the same commutation relation. Which will allow us to find its non-diagonal elements. Because if this is true, then doing the same calculation, we immediately obtain that the non-diagonal elements of this matrix L are of this form. This is only a part of the problem because we still need to find diagonal elements, but this is next task. Let us concentrate on non-diagonal elements first. For this, we should prove this commutation relation for this matrix. I should note at this point that this commutation relation is rather remarkable and in some sense fundamental in the theory of integrable many-body systems. In more general forms, something like it appears for more general models. For example, for trigonometric Cologner-Moser model and Rusinard-Schneider type models, but not in elliptic case. In elliptic case, this no analog of this relation is known. But in rational and trigonometric cases, these relations always exist and have rather interesting meaning in another approach to many-body integrable systems, which is called, and in this interpretation, this relation is called momentum, angular momentum condition. So this is approach related to Hamiltonian reduction. This is a very general method. Maybe later we will discuss it very briefly. And you can find some information about it in Perelomov's book, for example, and in many other reviews on the subject. You can find them in the ePrint archive for just searching for Hamiltonian reduction. Okay, so let us prove it. The proof is rather direct calculation. We write this, substitute this, multiply this equality by v to the -1 from the left and by v from the right. Then we express x in terms of matrix v and write you see that commutator of this term with this term is 0 because they are the same matrices. So we can cancel it, and we are left with okay. And then we use this commutation relation. So we have G V I minus V. And let us represent this matrix E in terms of this vector. Then it can be written as matrix product of non-square matrices as follows: E times transposed E. So this is a row vector with matrix elements 1. And we multiply it by column vector with matrix with components equal to 1. Multiply by the rule of matrix multiplication. This by this, and get this matrix with all matrix elements equal to 1, and this is just our E. So we, instead of the C, we write this. And now we can use this normalization condition. So we rewrite it as E minus V times E. This is E. But we are left with E transposed and V, yes, V to inverse V from the right. Now we should notice that the diagonal elements of the left-hand side are 0, because it is a commutator of diagonal matrix with some other matrix. Such commutator is always 0. Diagonal elements of such commutator are always 0. So matrix diagonal elements of this matrix must be 0. But what they are? It is 1 coming from this identity matrix minus, let me write it in this way, E so this is ith element, EI L E T L J this vector. We should find this is, but this is a matrix. It is matrix E times V to the minus 1, and we should find its diagonal element. What is it? It is, by definition, sum over L E I L V minus 1 L E. But this is 1. All of them are 1. And so we can write that L E minus 1. And this should be equal to 0, because, to 1, to cancel this one. And this just means that E t times v to the minus 1 is ET. Because if we write this in matrix elements, we have E L v minus 1 L E multiplication from the left. Sum of L, and these are all 1. And so we have this equality. Okay, so we can erase this matrix, and we get the same commutation relation. So we, in this way, we find non-diagonal elements. How to find diagonal elements now? For this, we differentiate this equality in time. Take time derivative of this. What do we get? In the left-hand side, we get just 2 L naught, minus 2 L naught. And on the right-hand side, we have v dot x minus 1 plus v x dot e to the minus 1 minus v x e to the minus 1 v dot v minus 1. Let us denote v to the minus v to the minus 1 v dot, this matrix, let us denote it by m. It depends on time, and it will be just the second member of the Lux pair, M matrix, for the Lux pair of the Calogero-Moser model. But at the moment, we still don't know this. We just introduce some notation for this matrix. And in terms of this matrix M, what do we have? We continue this equality. Oh no, let us multiply both sides by v to the minus 1 from the left and by v from the right. Then here we have minus 2L according to where it is. We introduced matrix L as v to the minus 1 and not v. So this is minus 2L, and on the right-hand side we have this one gives minus mx. This one is just x dot, and this is plus x m. So we have a relation. And this relation allows us to find diagonal elements of the matrix L, because diagonal elements of this commutator are 0, because X is diagonal matrix. So we are left with this, and this means that L I diagonal elements are just minus 1/2 xi dot. Precisely what we need to obtain. So in this way, we proved that L defined by this formula indeed is the Calogero-Moser-Lux matrix. But how about M? How about M? Again, from the same equality, we can now determine, as far as we know L already, we can determine M from this equality, just in a similar way. To write it in matrix elements, both sides, and then on the left-hand side, we have Lij, where I is not equal to J. And on the right-hand side, we have X J minus Xi times Mij. From this relation, we conclude that Mij is 2Lij divided by Xj minus Xi. Now we should recall what is Lij and write it in the form 2J divided by Xi minus Xj squared. These are non-diagonal elements. What about diagonal elements? Diagonal elements can be determined from this normalization condition, because differentiating it in time, and using the definition of matrix M, we conclude that this matrix M acting to the vector E gives 0. Or, in other words, this means that M, the sum over all J, is 0. So we can express diagonal elements in terms of non-diagonal in this way. So non-diagonal elements we know. And this formula determines diagonal elements. And you see that they are just what we had previously when we introduced Lux pair for the Calogero-Moser model. This matrix M, which we obtain in this way, is just the same as it was previously. Now, the last step is to establish Lux equation, from which equations of motion will follow. This is quite easy. We should just differentiate this equality in time. We take derivative and get, taking this derivative, we have minus v minus 1 dot v minus 1 not v plus L naught is constant in time, so we don't differentiate it, and using the definition of matrix M, we can rewrite it as commutator of M and L, because this is L. So we have obtained the Lux equation. This completes the proof. because we already know that this Lux equation implies equations of motion of the Calogero-Moser model. Okay. I explained this proof in some in so many details because I believe that this statement is very important, and this proof should be properly understood before we move further. In other cases, in more general cases, like in the trigonometric case, there exists a similar projection procedure which allows one to linearize equations of motion in some larger space. In those cases, I will not show you the proof and leave it for you for homework and for problems for examination. And now the next goal is to generalize this previous theorem to higher Hamiltonian flows of the Calogero-Moser model. And the statement is that consider the matrix of the following form. In the previous case, k was equal to 2. And this corresponds to the flow with Hamiltonian hk, which is trace of L to the k. And again, the statement is that eigenvalues of this matrix as functions of time move according to this Hamiltonian flow. To distinguish different flows, it's convenient to write here additional index, just having in mind that each flow depends on its own time. We can introduce its own parameter for each flow, and these are this time. So in the previous case, the time was t2. This proof is rather longer and more complicated. That the proof for k equal to, and I will not show it in all details, leaving them for you. But let us just begin, show the beginning of the. For this, we need first we need to write explicitly the Hamiltonian equations of motion corresponding to one of these higher flows. By definition, it is this is our Hamiltonian expressed in terms of momentum. So our momentum is connected with velocity in this way. So diagonal elements of the Lux matrix are just momenta. Now let us take this derivative And this is due to cyclic property of the trace, we can write it in this form. In general, when if there is no trace here, then we should write this as a chain of as a sum of k terms, because this is the first term, this is the second term, and so on. So we should differentiate each multiply and sum them. And the order is important because this derivative in general doesn't commute with the matrix itself. But under the trace, due to the cyclic property, we can write it in this way. Taking this derivative, because pi momenta enter only diagonal, and there is no momenta in non-diagonal elements, so this is equal to minus k, k minus 1, diagonal element. The second part of the Hamiltonian equation says like this. So we should find this derivative explicitly. This is a problem for you. And the problem is to prove the following identity. Where this matrix EI is the diagonal matrix whose all elements are equal to 0 except the elements, the ith elements of the diagonal. So we can write it, its matrix elements as delta AI delta BI. And M is the second member of the Lux pair. Using this, we can write this as using these relations, we can find the derivative of the Lux matrix. And the result is as follows. These are diagonal elements, and in non-diagonal elements we have the following. The next step is to now I will not go into the details. Just say probably in words. The idea is the same as in the previous proof. One should introduce the matrix which diagonalizes this one. Let us call it again V, but now it depends on K. Depends on this K and on time. So we should try this. Again, this definition of the matrix V. Again, there is a freedom in its definition, and this freedom can be fixed by the same condition. Now, everything will follow from time derivative of this relation. And again, we introduce matrix L by the same formula, but now this matrix V has index K. And the statement is the same, that this matrix L is the Lux matrix at the time tk, when axes move according to this higher Hamiltonian flow. And the second relation is time derivative of it. It gives Lux equation for the higher flow. Combining these two relations, time derivatives of this and this, you can proceed in a similar way as in the previous proof and find matrix elements of mk, which is minus v, as v similar definition, and prove that the Lux equation for the higher flow with this matrix mk. This is rather long calculation. I will not show it for you now. You can see it in the lecture notes, which will appear on the site, and try to follow this calculation and repeat it. By the way, in the process of this calculation, you will need to prove some identities. And these are problems for homework. Okay. Now let us discuss the last topic related to the rational Calogero-Moser model, and this topic is duality, or in this case, self-duality. There are different types of dualities in integrable systems. And this is what makes the theory of integrable systems rather beautiful. Existence of such relations between non-obvious relations between different kinds of models. This is what is called duality. The duality transformation relates one system to another system which may be very different. And vice versa. You can start from this second system, apply the duality transformation once again, and obtain the first system. This is not a chain of transformations if you apply it many times, but this is a how it is called, such operator, square of which is identity. It has some name. Involutive. Involution. This is duality transformation. There are at least 3 different types of dualities known in integrable systems. And now I will discuss only one. And among all integrable models, there are some distinguished models which are self-dual. So applying this duality transformation to this model, you get the same model. And rational Kalodzer-Moser model is one of them. What is duality transformation? This type of duality transformation, which I'm going to discuss. It has another name. It is sometimes it is called action coordinate duality. Because action, in classical mechanics, there is the general approach to the system is to linearize its dynamics in terms of action angle variables. Action variables is a specific sort of conserved quantities. In our case, we understand by action variables, we understand eigenvalues of the Lax matrix. They are conserved quantities for any flow. These are action variables. And coordinates are just coordinates of the particles. And this duality between x coordinates and eigenvalues of the Lax matrix, this means that there is a transformation which sends coordinates to eigenvalues of the Lax matrix, and in this new model, the eigenvalues of the Lax matrix, which were conserved quantities, become coordinates in the new system, and vice versa. These xi's become eigenvalues of the Lax matrix of the second system. To be more precise, let U be matrix which diagonalizes the Lax matrix. So we can write it in this way. This L tilde is diagonal matrix with eigenvalues lambda 1, lambda n, which are conserved quantities, integrals of motion. Again, there is a freedom to multiply it from the right by diagonal matrix, and we fix this this freedom by the same condition. Let us now put x tilde to be equal to the way in this way. X was diagonal matrix, and this one, x tilde, is already non-diagonal. It is a direct verification that this commutation relation, which was characteristic relation for the Lax matrix of the initial system, under this transformation, it becomes the same in the variables with in the matrices with tilde. But now the matrix L tilde is diagonal. And here, this X was diagonal. Here it was on the first place, and here this diagonal matrix is on the second place. This is a direct calculation. You should apply this matrix U from the left, from the right, and use the same argument as before in the previous proof, the same argument with the matrix V. So this relation allows us to find matrix elements of X tilde. Just writing it in matrix elements, and the result is that X tilde ij is some psi I, some diagonal elements which cannot be determined from this equality, plus non-diagonal elements which follow from this commutation relation. You see that this form is very similar to the form of the Lax matrix. The only difference is that in the Lax matrix there were minus signs here and here. So the variables lambda I are called dual coordinates. And these variables xi, which are introduced by this formula, it should be noted that they are determined already by this definition, because matrix U is something. It's defined by this relation, and so X tilde is defined. And diagonal elements are also defined by this relation. So they are something. They are expressed somehow through original variables. So lambdas are expressed somehow in terms of original coordinates and momenta. And so this xi are also some maybe non-trivial functions of the original variables. And they are called dual momenta. And the transformation from original variables to this is called duality transformation. And the dual Hamiltonians, which are defined as traces of k power of this matrix, define some dynamics in this dual model, and we will the next what we will do, we will show that this dynamics is the same as, in terms of these new variables, dual, is the same as the original Calogero-Moser dynamics. Because of this, this model is self-dual. And in the dual model, X tilde plays the role of the Lux matrix. The proof, for the proof, you need to know some basic facts on classical mechanics. Just Hamiltonian approach to mechanical systems. Namely, consider the two forms. As you probably know, the symplectic for the definition of the Hamiltonian model, you should have some symplectic structure on the phase space. And in our case, the symplectic structure is standard. And in terms of matrices, it can be written in this form. It's a rather simple verification. Just write this in matrix elements, and you will see this. Now, let us consider another form, omega tilde. Which is made of dual variables. It is to form on the same phase space, because this psi's and lambdas are some functions of pi and x. Of course, it is expressed through this matrices in this form. And the proof consists in the statement that these two forms are equal to each other. This just means that the transformation is canonical. But this transformation, duality transformation, is canonical. And so this already means that this dynamics defined by this Hamiltonians is the same as Calogero-Moser dynamics. I should note that in the literature, the duality transformation of this type are sometimes are called anti-canonical. The anti-canonical means that this form is equal to this one up to a sign. So omega is minus omega tilde. But the difference is rather trivial. I prefer to think of them as canonical transformations rather than anti-canonical. And the question is in sign of this, the definition of this dual momenta. If you define it with minus sign, then the transformation will be anti-canonical. Another way to say this is to find Poisson brackets of the dual variables and prove that they are just delta ij, the same as for this canonical variables p and x. This is equivalent statement, equivalent to equality of these two symplectic forms. To prove it, we need some technical lemma. Let x and y be two quadratic matrices of some size, n by n. Introduce x tilde, and also there is some invertible matrix U of the same size. Introduce x tilde as ux the minus y, made a similarity transformation with this matrix U, and the same for y. Y tilde is u y u to the minus 1. Then the lemma states that the form is expressed through the same form for x and y in the following way. And there is a correction of the form to prove this identity. This is an identity valid for any x and y, x, y, and u. To prove it is a problem for homework. It's a rather technical calculation, does not require any non-trivial ideas. And using this identity, we can prove that, and using this representation, we can prove that omega is equal to omega tilde, because x tilde here and L tilde are just similarity transformations of x and L with the help of the matrix U, which diagonalizes Lax matrix. So to apply this lemma to that case, you can prove that omega is equal to omega tilde. In other words, you should prove that this correction is actually zero for those matrices. I leave this problem for you for your homework. And now let me start discussion of another model. Maybe some at this point some comments on the duality is useful to do. Or maybe it's better to do this later when we will be more familiar with other models, such as trigonometric Calogero-Moser model, elliptic Calogero-Moser model, rational Rusinard-Schneider model, trigonometric Rusinard-Schneider model, elliptic Rusinard-Schneider model. And this duality transformation between these models is like this. This one is self-dual. And this one is self-dual. But these two are related by duality transformation. No. No. No, yeah, okay. Yes. A very interesting question is, how about elliptic models? And this is now is actively discussed in the literature. And the unsolved problem is to find elliptic self-dual model. We have rational self-dual model, trigonometric self-dual model, but elliptic self-dual model is not known. This is an open question. Okay, maybe I will discuss it in some more detail later when we become more familiar with all these kinds of models. And now the next topic is rational, again, rational Calogero-Moser model, but in external potential. It turns out that the rational Calogero-Moser model admits a generalization. You can add here quadratic potential. And the model still remains to be integrable. So these are Calogero-Moser particles on the line, but in external potential, which does not allow them to come to infinity. So they are confined here in some region. Equations of motion which follow from this Hamiltonian is like this. As it follows from these equations, when you take a sum of them over I, full of them, then this term cancels, and this term remains. It will be 4 omega squared times coordinate of center of mass. And so you see that now the center of mass is not, does not make free motion, but just it moves like harmonic oscillator in this quadratic potential. This model also has commutation representation of the Lux form, but there are important differences. Let us introduce matrices, two matrices, L plus and L minus, which are L defined in the same way as in the previous case, plus minus I omega x. The problem for you is to show that the equations of motion are equivalent to the following matrix equations. M is the same M matrices and as for omega equal to 0, plus minus I omega L plus minus equal to 0. Now consider two matrices, L1, which is a product of L plus and L minus, and L2, which is the same product but in different order. So this one is L squared plus omega squared x squared minus. And another problem is to prove that these two matrices, L alpha, where alpha takes values 1 and 2, already obey the Lux equation. And of course, their sum also obeys the same Lux equation. Let us denote it as this letter. So this is L1 plus L2. And it satisfies the same Lux equation, and we can immediately see that the Hamiltonians defined in this way are conserved quantities. And they define higher Hamiltonian flows. It can be proved that all of them are in involution. In fact, I don't know exact literature where this statement is proved. Maybe some references you can find in Переломов's book. At k equals to 1, we get this Hamiltonian of the original system. Another problem is to find explicitly H2. Now, from these equations, we can find that if we write what we get, the question is, what we get if we try to calculate this expression, which was 0 for previous model without external potential. And if the matrices L and M are the same, and what is this in this model with external potential? And from that commutation relation, we get the following. But the imaginary part should be 0, because this is real, so this is purely imaginary. So all this must be equal to 0. And from this we get the following relation. And then it follows, so this is equal to 0, so L dot plus commutator L and M is just 2 omega quadrat x. When omega equals 0, we return to the original Lax equation. Okay, at this point we finish today's lecture, and in the next lecture we will see how to generalize a projection method to this case for the model in external potential. And instead of linear motion in the matrix space, whose projection leads to Kalodger-Moser dynamics, now we should consider harmonic motion in the matrix space with frequency omega. So instead of the matrix X naught minus 2T L naught, we should consider matrix X naught cosinus of 2 omega T minus L naught sinus 2 omega T divided by omega. When omega tends to 0, this matrix tends to this one. And again, consider dynamics of eigenvalues of this matrix, and the next time we will prove that they move according to equations of motion of this Calogero-Moser model and external potential. Okay.